Okay, so I'm going to work out the solutions to homework number 1, Electrical Engineering 575, for spring 2021. So let's do the first problem. So the first problem asks us to find the two things with respect to a 12-pole synchronous motor. Let me zoom in on that a little bit. Okay, so we're doing this problem here. What is the rated synchronous speed in radians per second? And what is the rated mechanical rotor speed in revolutions per minute? So we have a synchronous machine. It has 12 poles, and it is excited with an electrical frequency of 50 Hertz. So this means that it's a synchronous motor. There's a drive upstream. Doesn't have to be a drive, it could just be a power source, but normally synchronous machines are operated with a motor drive. They're rarely operated in a different, right off of the line. They're almost always operated with a drive of some sort. There's your synchronous motor. So when we say, obviously, it's a 12-pole motor. I'm not going to try to draw 12 poles. But when we say the motor is excited with 50 Hertz, that means that the drive voltages, VA, for example, has some peak voltage, cosine omega E t, and VB, some peak voltage, cosine omega E t minus 2 pi thirds or 120 degrees, and VC is V peak cosine omega t minus 2 pi thirds. And the voltage that you could say measure coming off of the drive line to line is, this is VAB, VBC, and VCA, where VAB is the difference between VA and VB, VBC is VB minus VC, and VCA is VC minus VA. So those are the line-to-line voltages. So the question is asked, what is the synchronous frequency? Well, we have a resultant current in the machine, IA, be some I peak cosine omega ET, plus some power factor angle. IB is I peak cosine omega ET plus the power factor angle minus 2 pi thirds, and IC is I peak cosine omega t plus phi power factor plus 2 pi thirds. So we can go to the up here onto Canvas, and let's look at something here to help us understand what's going on with the synchronous machine. I'm just really doing this to remind you of a few things. I'm not necessarily the solution to the homework problem, but I'm really trying to make it understandable to you what's going on. Any three-phase excited machine will result in what we would call a rotating MMF. And in these animations, there's a number of representations of that. Probably the best one, let's see if I get it, pick the right one here. Let's see, we've got, it might be yep, this is it here. This is my favorite picture. So I told you that we had phase A. These are currents. Phase A current is red. Notice what's happening. It's a sinusoidal excitation current. It looks like a and what's happening here is each one of those little circles that you see represents current flowing in a conductor. And you can look at the x-axis. This is an angular position. And so you've got starting at 0 and then going to 360 degrees. So it's like you've just flattened and stretched out the inside of your stator windings. And everywhere you see a circle is a slot that, well, it's a point. It's actually not a slot. It'd be a lot more discreet looking if we were looking at slots. But each of these circles are a current point at a position along the stator. And so if the current in that position, so we could watch like 30 degrees. I'm looking at the red one. So 30 degrees, it goes up to almost 1 at that point, comes down to almost -1. So it's going back and forth at that point. That is the MMF associated with phase A at the 30 degree point. You can go to another point, say the 180 degree point. You can see at the 180 degree point the MMF hits a peak, goes up and down at that peak there. And this is really because we're saying that the MMF is a cosine function that has a peak at 0. For phase A, the peak is at 0. If you look at phase B, because it's spatially displaced the way the windings are distributed, the green winding shows it's going up and down, and it's hitting its peak at 120 degrees, see? It goes between 1 and -1. And then the blue one is, the peak is happening at ±240. Well, what's happening, these currents are varying at each position between 1 and -1, but the MMF sums up to this black line that's rolling across the screen. You can think of that black line as a magnetic flux or magnetic MMF. I keep trying to make this point that the flux and the MMF are proportional to each other. Simply, they're different from each other from whatever the reluctance of the machine is. But the fact that that little sine wave is moving across from 0 to 360 means if there were a magnetic field on the rotor, a permanent magnet or a wound field on the rotor, it would pull that right with it, and they would stay in lockstep with each other. There would be an angular difference dependent on the load, but they would be pulling this black moving sine wave would be pulling the rotor at a rotational speed. So the rotational speed I'm talking about, that is the synchronous speed. That's the speed of the flux, the resultant flux from the MMF of the stator moving at a synchronous speed. And then there's another picture that will show it rotationally. There's several. I'm going to try to find it here. Well, here it is. Why I'm getting lucky here. On the right is the same picture I just showed you. On the left, it's showing them as space vectors. And notice that you've got this red A-axis, and a little red arrow is going from between positive and negative along that. It's the x-axis. You've got 120 degrees. You've got the b-axis of green. It's going positive and negative along that axis. And then you've got the blue, 240 degrees there, and that's going positive and negative, but they all add up to this black thing, this vector that's moving. That is the movement of the MMF from the applied stator excitation, and that's the magical thing that's pulling your magnetic rotor in a synchronous machine, and the rate at which it's moving is the synchronous speed. And that synchronous speed in the synchronous machine is exactly the mechanical speed. I hope this is clear. Okay, so then the answer to the question to find synchronous speed from the electrical frequency and the number of poles, the synchronous speed is 2 over poles times the electrical excitation frequency in radians per second. This is omega E is equal to 2 pi times Fe. That's the relationship to that electrical frequency, 50 hertz. Well, where does this come from? It comes from the equation that relates the synchronous speed to the electrical frequency. Basically, it says that I've got, let's say I start out and I have a rotating MMF that's rotating at a speed, synchronous speed, omega s. It's going to be multiplied or increased by this factor poles divided by 2, or pole pairs. Okay, so that's simply how you do it. So the synchronous synchronous speed, I like to say speed, is 2 divided by 12 times 50 times 2 pi. So let's work that out. Okay, so this tells me that I've got 8.33 radians per second. 12 poles, 50 hertz. Oh, I forgot to multiply times 2 pi. I knew that was wrong. So I have 52.36 radians per second now. Okay, so that's the answer to A. The answer to B, we go back, what did the question ask us? What's the rated mechanical rotor speed and revolutions per minute? So I told you earlier that the speed of the rotor and the synchronous speed are the same in a synchronous machine. And so the mechanical speed is the synchronous speed. To convert that into a RPM, we usually call this N, and I could say this is N sub S. And same thing as what we might call N. They're equal in a synchronous machine. If it was an induction motor, as opposed to a synchronous motor, then these two things would not be equal to each other. So I'm going to do this conversion factor, 30 over pi times the synchronous speed. And where did this come from, you might ask? So remember, we're trying to convert to RPM from radians per second. So you got, it's revolutions per minute is what we want to try to get to. If we started out with radians per second, one revolution is 2 pi radians. So I'm going to multiply this times 1 revolution and divide it by 2 pi. 1 minute is 60 seconds. So I'm going to multiply this thing by 60 seconds and divide it by 1 minute. Seconds cancel out. This is radians. Radian is unitless anyway. And I'm left with 60 over 2 pi, or 30 over pi. So this is, in this class, doing this conversion back and forth should become second nature to you. So that's not problem number 1. Problem number 2 is a DC machine. This is what it's asking. Under a rated mechanical rotor speed of 1800 RPM with rated field current excitation, a DC motor is operated as a generator, and then a line-to-line voltage at the armature winding terminals is measured to be 400 volts DC. The first question is, what is the synchronous speed? This might be a bit of a tricky question for everybody, but I want to remind you of something. Here's your DC machine. These little arrows here are exactly equivalent to what we were talking about. They're MMF or flux arrows showing the movement of that flux as the rotor spinning. So the red line here is exactly the same thing as that black line that we were looking at for the synchronous machine. So it's the armature. The armature for the DC machine or DC motor happens to be on the rotor, not on the stator. There's this brush and commutator mechanism that makes this thing behave the way it does. But notice that the MMF, magnetic field flux, is green and the armature flux, or MMF, which is red, they're both fixed in space. They're not moving. So what would be the synchronous speed? It would be 0. Okay. So the first, synchronous speed of a DC machine, a DC motor, is 0. Now B, that requires us to think about what the information we have is telling us about this problem, and as well as C, what's the rated mechanical rotor speed. So, but we're asking that in radians per second, because otherwise it's like, didn't you give me the mechanical rated speed? Yes, I did, but it was in RPM. So we're just going to convert it back to radians per second. So what we have is the mechanical speed in radians per second will be equal to pi over 30. Basically, it's the inverse of this thing, because we're going the other direction, times the mechanical speed, which is n. Notice I'm using n, not ns, okay? This is the only motor of the 3 motors types that we talk about where synchronous speed and rotor speed are equal. They're definitely not equal in a DC machine, or a DC motor. Sorry, I keep saying machine because I'm used to teaching this generally as a generator or a motor, but we're only talking about motors here. NS is 0. N, which is the actual speed, is 1800 RPM. So these two things are definitely not equal to each other, right? No, they're not. Okay. Pi over 30 times 1800 RPM, and that tells us what that mechanical speed is in radians per second. And that's 188.5 radians per second. Okay, there's one more problem. One more question. What is lambda AF? Okay, remember that in the DC machine, if we look at the steady state equivalent circuit, the DC motor, sorry, it looks like this. So we have the applied armature voltage, the armature current, RA, and we have EA. EA is equal to lambda AF times the mechanical speed. If we were operating this thing as a generator, which is what it says in the problem at the beginning, it says the motor is operated as a generator, and then the voltage across the terminals of the armature winding is measured to be 400 volts. All you have to do to operate a motor as a generator is to spin it from some other source. So essentially have, say, a synchronous motor right here. We're going to put the 3-phase power into this synchronous motor so it can turn this shaft. We're going to connect it up to a DC motor, and we're going to run the DC motor as a generator, and we're going to measure the armature voltage VA, and that was 400 volts. What we just did was we're looking at it when it's a generator. It's open circuit. If there were a load, let's say you put a little load here, the current would go out in the other direction. That's the only change to the circuit when you run it as a generator. But we're at open circuit, so EA is equal to VA because IA equals 0 when it's not loaded. EA is lambda AF times omega M. So since I know omega M and I know EA, that's equal to VA, then lambda AF is equal to what we measured, the VA open circuit, divided by omega M. 400 volts divided by 188.5 radians per sec, and that is equal to, it's almost a little more than 2, right? 400 divided by 188.5 is 2.12 volts per radian per second. Radian's unitless, so we can pretty much ignore that. It's 2.12 volt seconds. In EE362, you're taught that that is also what's called a Weber. Okay, so now we've done problem 2. And on to problem 3. Okay, so let's take a look at the third problem. This is a DC motor drive problem. Really to try to help you synthesize what we've learned about DC motors, and then from a, let's say from the application perspective, what you're going to drive, what kind of load the motor is going to drive, and then picking what kind of electric drive you need for the motor. So what we've given you is we've given you the shaft horsepower of the load. This would be like a load requirement. We've already picked a mode, but the other load requirement would be the speed, 990 RPM. And then we've already picked a motor. We'll say that's at 170 volts is the rated voltage of the motor that will give us that speed. And we can load it up at that speed and achieve 7.5 kilowatts of power at the load side of the shaft. Now the motor has parameters that are given to us on, say, a data sheet. We've got a armature resistance, we've got lambda AF, which is essentially what can be called your back EMF constant. Again, we've learned in class that lambda AF is the mutual flux linkage between the armature and the field. That's the mutual inductance times the field current. And we also have learned recently in class that in the textbook, Christian's textbook, he's referring to this as KB. But if you can't make this connection here, you're going to be very limited in your application of this knowledge. The other thing that we've been given as a parameter is B, which relates to the rotational losses of this machine. And basically we're saying that the only rotational losses that we're concerned about are viscous or damping losses. Kind of like a rubbing that's not sticking on the bearings as this thing's moving around. That's a way to think of it. I guess you could think of it as you got oil up the mechanical bearings mechanism to keep this thing rotating smoothly, but there's a little bit of loss or drag associated with the oil in the bearing. That's what this B would be. I hope that's like ad nauseumly clear to everybody at this point. We're also saying that we have a motor drive and it's running off of a grid, an AC, three-phase AC grid at 208 volts RMS, 60 hertz. Since it's running off of the grid, there has to be a three-phase full bridge rectifier front end to this drive, and then since it's feeding a DC motor, there's got to be a DC to DC converter with a large DC link. So I've described everything, and I'm going to write out, make a little diagram of what we're talking about. What we have here is we've got a three-phase AC supply. We just start from the feed end and go all the way to the load, motor load. You've got a feeder here of some sort. Maybe you're building, you're going to go connect up to, there's a 208 volt feeder. Pretty common in buildings, because if you take this as your neutral and you were to run one line of this voltage somewhere else, so let's say, this is just a little side note, but let's say you wanted to run a little single phase load, you could connect it up to this, find a good, whoops, try to find a good color that I'm not using. There's a single phase load, and it's going to get a voltage of 208 divided by square root of 3, which happens to be 120 volts. So that's your standard household, or plug in your alarm clock in the hotel room. Most hotels have 208 three-phase distribution, the big ones. Okay, now what you've got is you've got a feeder, so there's probably a circuit breaker or disconnect switch that you can open and close, and now you're going to connect up to your drive right here. This is the drive system. There's a lot of things inside of this drive. You've got to have some kind of a little circuit here that is going to limit the inrush current when you connect up to a fully discharged motor drive. That's because you've got a big DC link capacitor at the other end here. So you're feeding into this thing, And I should note that there's always some impedance of this feeder in your wires or in your transformer. So there's some upstream impedance here. Here's your first power electronic converter. It's just a passive diode bridge. Connects to the 3 phases, and then there's a big, what we call DC link capacitor. And now what we've done is formulated a DC bus, because we're using what's called a voltage source converter to drive our motor. So that means that it has to have a very stiff voltage, a voltage that won't move very for all intents and purposes. This voltage is going to hold very, very rock solid, steady. And that's the voltage input to our DC to DC converter. And then we've got typically this is a 4-quadrant DC to DC converter drive. These are IGBTs. It's this like ubiquitous thing, that horrible word that's out in the industry today. You can buy for if this was a, I think in the currents we're looking at, you could use IGBTs. If you have lower currents, you could use MOSFETs, and those would be discrete devices. But these come in these little 2-pair blocks. They're called a half-bridge module. Most motor drives commercially have these in there. And there's your connections to your motor. And then your motor has a shaft, and you've got a load. The load under rated conditions, T shaft rated, is equal to 7.5 kilowatts. So there's our motor, there's our load, and here is our drive. Oh, there's one more thing in the drive I forgot to mention. We have a field that we've got to control. Kind of annoying to have to deal with this, but because it's not a permanent magnet machine, but that field is going to be handy to us at some point. So I'm going to conclude it in our discussion here. That's the other part of the drive and the other part of the motor. So this is going to go into what's called a phase-controlled rectifier. Looks like a diode bridge, but it has SCRs, or thyristors. SCR means a silicon-controlled rectifier. It's a gate. You use these little gates here to control the conduction of the effectively diode. So that little thing right there is a thyristor, or SCR. Now this particular converter, it works very good with what we call current source conversion. or current based conversion. So this is actually feeding a very big inductor, which is your field. There's no capacitor involved. So there's your big inductor right here. I'm trying to put it close to the motor. It has a big inductance and it has a pretty sizable resistance. That's your field. And it's being controlled. And the voltage here, VF, is the voltage that gets applied to your field, and it gives you a field current. And the voltage here is the armature voltage, VA, and then there's an armature current. These two things are decoupled from each other. We had shown the picture in problem 2 that, what does the motor look like? It's got the field windings here that's associated with everything I've got highlighted in green. This rotating shaft with these brushes. We've got the you've got that figure we showed the lambda field. I would call this is you could say this is lambda F, or I'm going to call it lambda AF. And then we have because we've got a bunch of little slots with windings here. X, hand goes in, right hand rule, fingers come out the bottom. Thumb goes to the left. There's your I would call this your F of the armature, which is some effective turns times the armature turns. But it's also proportional to what we could call a armature flux. So there you have it, right? So this stuff is all connected, right? There's a shaft on the end here. That's your mechanical system, and it's trying to move a load. You probably got some bearings in here that are giving you the B that we talked about, the losses. And those losses relate to torque loss, or what we call rotational power loss. Remember that in the mechanical world, P is equal to torque times speed. And just like we have the electrical world, P is equal to volts times amps. There's all these analogies that help us out. If we can go back to the electrical circuit, we could probably understand almost everything in the world. That's why we're electrical engineers. Okay, so let me put this box around here again. There is your motor drive. All these pieces needed to control this DC motor. Okay, so that's your background. Question being asked is, first of all, what is the maximum speed of the motor when the load on the shaft, the T shaft, is set to 0? We're not employing what's called field weakening, which means that we're not going to do anything to the field circuit. We're just leaving it in the nominal condition. That really means that lambda AF equals 1.5, because we can change that if we need to, but we're not doing that. And often it is changed to operate at higher speeds. So then we're also specifying a max duty cycle of the drive of 0.8, or that's D equals 0.8. So we should be able to find the maximum speed of the motor drive, of the motor, that we can operate with this drive quite easily. To help us out before we start getting into the actual solution, let's write down what we know about this system. So we know that the rated armature voltage is 170 volts. We know at the load end that the shaft rated load, that would be the same as saying rated torque load, is 7.5 kilowatts. Let me double check that. Yep. Okay. We've got on the load requirement, we've got a speed, rated speed. Let's see, what was it, 1800? My memory's bad here. No, it's 990 RPM. Okay, so we're running 990 RPM. We've got some mechanical loss that has been quantified for us. That's 0.05. The units are often helpful here to help us understand what this is. So that's it. What does it tell us the units are? It says a Newton meters second per radian. That's a very interesting set of units. Newton meter seconds per radian, or you might just say Newton meter seconds because radian is a unitless thing. It's 0.05, not 0.5. 0.05. We know on the motor end we've got an RA of 0.26 ohms, and we had a lambda AF of 1.5 volt seconds. Double check that. Yep. Okay. Almost everything. On the drive end, we'll basically have a input line voltage here, line to line, 208 volts RMS, 60 hertz. So, first of all, why don't we just work this from left to right, and we need to find out, before we do anything, what is the voltage, the DC voltage into our DC drive, because that's really what's important. This front end stuff is there, unless we were running off of a DC source, like if it was in your car and you had an alternator that has this, it actually has this little thing integrated into your alternator in your car. So it puts DC voltage out to the car. If you're on a ship, there's a lot of ships that use DC now. They rectify right off of the generator and send it around everywhere. But most of the time, most of the things you're going to see are going to have AC coming in. So we have it there for a reason. Now, I've told you that because we've got this large capacitor rectifying this, and I'm ignoring the impact of this line impedance, then we can come up with a VDC rated of our motor, which that's the VI that we're going to be considering, is the peak of the line to line, square root of 2 times 208, which gives you about 294 volts DC. So we've got, this drive information here. We've got the armature information here. We've got the mechanical information here. The first question asks us, what is the maximum speed that this drive can put out that the drive can, I'm going to call the drive plus the motor, can achieve. That's what we want to find out. Now what it is, it's limited by the drive. And we are going to say that without modifying the nominal field conditions, because that's what it said when I said running at rated. That means you're running at lambda AF rated, which is what we gave you, 1.5 volt seconds. And that means that our field winding, which has this mutual inductance to the armature, very huge inductance, but it's running at some rated nominal field current. Okay, that's what we're saying right now. What is the max speed? And we have a D max equal to 0.8. So we know that the armature voltage that can be put out by this drive, it's a simple buck converter, so its VA is equal to whatever the duty cycle is times the input voltage VI. So that's going to be D max times VDC rated. 0.8 times 294 volts. This tells us the maximum voltage, and that maximum voltage will correlate to the maximum speed that you can achieve. 0.8 times 294 is 235.2 volts. So we have this important interim answer, but the thing that we're trying to understand is what is the maximum speed. Now in the mechanical world, there's probably something equivalent to an electrical equivalent circuit, but we don't have equivalent circuits, equivalent electrical circuits. We're electrical engineers. That's the only way we understand the world. We've got to have some kind of circuit. So we have to actually use the differential equation, differential equations associated with the mechanical circuit. This is what I use. Okay, there's probably some expression if I was a mechanical engineer, but I don't need to know it. I don't really care about it. Okay, but I definitely care about the dynamics of everything I'm working with. And so that is related to these things. So we always care about that. We've shown that we know that the speed is equal to some inertia value times the acceleration of the speed, and minus, let me see if I got that right. Yeah, sorry. We know that the electrical torque produced by the motor is going to be equal to the inertia times the acceleration. And then if there is any load, we've got to add on to this. So this thing's got to supply everything. So let's just say you had a completely perfect shaft. There was no bearing loss, no friction, nothing, no viscous damping. Then the only thing the electrical, and you don't have a load on the other end. So we're at no load, because the question of A was, we're talking at TL equals 0. That would be everything. However, we have a torque loss on the shaft, and we've got a load, right? So this is TL equals 0. What is this? Well, we've explained before that this would be equal to B times omega M. Let's look at this in terms of the differential circuit. We want to understand the differential circuit, so let's identify where are the derivatives. It's right there. We could replace this with what we've talked about in class, P, which is equal to d dt. We've got this also equivalency to the Laplace operator S j omega, if we want to look at things in the frequency domain also. But we're going to stick with this at the moment, and I'm going to move the derivative to the left-hand side and move everything else to the right-hand side so that I can get it in the canonical form of x dot, which is another way of saying the dot is a derivative. That's ax plus bu. And I don't have any inputs to the system, and that's what u is, right? It's 0, so it's really just what is ax. So it's d omega m t 1 over j te minus the B times omega m, because this was the damping loss proportional to speed, minus TL, which is 0. And I could write it, I could say this is the same as saying P omega m. And now I could rearrange this, and let's find this equivalence sign. That's going to be a summing junction. What is coming in is on there's an input. Now this looks like an input right now to the system as well. So I guess I have to be complete. That is an input. It's coming from the motor. We haven't tied it to any differential equations. So there's your input coming in, TE. So that's going to be the first thing, the first arrow. And then that's got a plus. Well, what's subtracting off? We've got the TL, but it's 0. And we've moved, it's got a negative sign. And then this is going to be the torque loss. Now in the steady state, well, first of all, I'm going to take everything that's summing up, divide it by 1 over j, and this is the acceleration. That's 0 in the steady state. 1 over p is your integral, and there's your speed, and then it comes back around here like this. So what we know is that this is, because that's 0, this is 0, so that's 0. So looking at it this way, we've got TE minus b, and then this happens to be the speed, this integral, right? You know an integral is always integral of, in this case say x dot dt is going to be x, but there's always some x that you were at initially, or steady state, right? That's really what this is. This is your prior point, so that's the speed, because this is 0. I'm kind of a roundabout way of saying it here, but we know now that TE is equal to B, and we want to run at a maximum steady state speed, so that's max. We want to know what that is, right? And so we also know that the torque connects back to the armature winding, and we want to work it back to the drive by this term here, lambda AF times IA. So there's going to be some current that is associated with that. Now what I'm not going to be able to put any numbers to this, so I'm just going to write everything symbolically so far to try to solve the final answer, because I'm trying to find this. Well, what this tells me is that omega m max is going to be equal to TE at T load equals 0, D max 0.8 divided by B. And that is equal to KA, or sorry, change the lambda AF times IA at T load equals 0, D max equals 0.8 B. So I'm going to save this little expression here for later use. So I'm going to stake it and put a circle around that, and then we're going to work the rest of the problem from the other end. And that simply is to say that if we, from the drive end, we know that VA is equal to D max times VDC. So we know what that value is. It's 0.8 times 294. That's from what we did. We figured that out up here, right? This is what our drive's going to be putting out under this max, under the D max condition. So that's 235.2 volts. We know what the steady state circuit tells us this. VA is equal to RA times whatever our IA is. Now we're going to say I'm operating it. Let's call this, instead of having to write that every time, I'll call that IA W max for now. Okay. Plus EA. So we know that this is IAW max, and EA is lambda AF, because we're running at the rated lambda AF. That's the 1.5 times the speed max. So now we have an equation that we can use. We have this equation here. I'll put VA over here, and we've got this equation here. What we're really after is this Wm max. And so it would be a good idea to take this equation here, this one here, and let's rearrange it in so that we can plug in the current as a function of the max speed. So rearranging IA at Wm max is equal to B times Wm max divided by lambda AF, and this is rated. So we got this equation here, and we're going to plug that into here, and we get VA is equal to RA times B Wm max over lambda AF R plus lambda AF R times Wm max. So we're after this variable here. We want to solve for that. So we're going to move everything to the left hand side, or basically flip sides here, and we can simply say Wm max, pulling it out of this whole expression here, is RA times B over lambda AF R plus lambda AF R equals VA. So Wm max would be equal to VA over RA times B lambda AF R plus lambda AF R. So it's good to check to make sure we did everything right by just checking the units. So we have volts on the top. We've got volts per amp here. Then we've got B, which is Newton meter seconds, over lambda AFR, which, remember, we could say lambda AFR has the units of volts sec, but also has the units of Newton meters per amp, because if we multiply it times the current, we get a torque. So we're going to use this one plus Newton meter per amp. Interesting. So we get this V volts. We're looking, this we're supposed to have on the other side radians per second, right? Or that's the same as 1 over seconds. So we got that. We've got volt seconds here plus Newton meters per amp here. So I want to use this one for that. This is a little exercise in just unit checking, okay? It's a little trick. If you understand what I'm doing, it's very helpful. 1 over seconds. But you want, if you do a big derivation equation manipulation, it's always helpful to check your units. So I got 1 over seconds and 1 over seconds. So I'm pretty confident in this answer. So this is the equation that gets me to that. So I'm going to plug in the maximum armature, the voltage at the maximum duty cycle, Dmax times VI. So that's the VI is the VDC rated, right? So we called it, I go back up here, yeah, VDC rated. VDC rated over RAB lambda AFR plus lambda AFR. Since we know all this stuff, I'm not going to make it any prettier than that. I'm just going to plug things in. So we had 0.8 times 294 divided by 0.26 times the B was 0.05 divided by 1.5 plus 1.5. That should give us our new speed. So we'll just calculate everything. So here's an interesting point. This factor here is because of the load, and it's light load. We could almost ignore it, the B, if we wanted, and then just have solved it without that, because it's really essentially this voltage divided by lambda, by the lambda AFR. And so that's 156.8 radians per second. So there's your max speed right there. Now so we actually did, going back to understand what we did here, the question was asking us to find the maximum speed under no load. But since I had given you this B factor, there are losses, so taking those losses into account, that should have made it so that we reduced the speed that we could get. This is a little bit of a low number, so I'm curious about it. But we can check that. So what we really said is neglecting the torque associated with the losses. So that would be the B times omega m max. We said that's approximately 0. The TE is equal to T loss. So we're developing some torque only because of the losses at light load. And if we said that this was approximately 0, then we're saying that TE is approximately 0, which would mean, since TA is equal to lambda AF times A, that would mean that IA is approximately 0. So we could also think of it as just a no-load test and get the same answer as what this is telling me, and say that the going around the voltage loop, VA, RA, IA plus lambda AF times the speed, and this is approximately 0 now. The speed I'm looking for is the max speed under no load conditions. So if you're totally confused, you can just do this, and you can take the VA, divide it by lambda AF. That's Dmax times VDC rated This is the rated lambda AF rated. And we get the same answer really from that. That's the same thing that we got up here. So that's the answer to this problem. The next problem is saying let's operate this motor at the maximum rated power, rated speed, voltage, and we need to find the armature current, the duty cycle of the drive. So we should be able to do that pretty easily. Armature current and armature voltage, which would give us the duty cycle. So the best way to do this is to start by finding the torque. Find TE. So the TE again is going to be B times omega M. Now it's under rated speed condition, plus the T load rated, which is what we're calling the shaft torque. Under rated conditions. And we know that TE is equal to lambda AF R times IA rated. So we know everything here. We can find this. So let's find that first. So the P shaft rated is equal to 7.5 kilowatts. Speed under rated condition is equal to 990 RPM. So I think we found that before, but let's convert this to radians per second. 103.7 radians per second. Take a little bit of a side trip here. We found that the max speed was 156.8. Well, what is that? This is maximum speed you can achieve without field weakening. We'll talk about field weakening very soon. So if I'm going to convert this to RPM, 156.8 times 30 over pi and it's 1497 RPM. This tells me I can get quite a bit of speed out of this drive if I'm not running under the rated condition. But under the rated condition, and if I can go to that duty cycle of 0.8, so we'll find out how far off we are there. Okay, so we know these two things. So then the shaft torque rated is going to be equal to the 7.5 times 10 to the 3 watts divided by the speed, 103.7 radians per second. That's because we know that that's the P shaft rated divided by the rated speed will give us the torque, and that is 72.3. I purposely stuck with pretty close to the numbers we've been doing in our example in class. Okay, so that's the rated shaft torque. The B times the rated speed is what? 0.05 times 103.7. This should be a really small number if the last answer was right. 0.05 times 103.7, 5.19. So the total torque that we need is going to be 5.19 plus 72.3, which is about it's 77.5 Newton meters. And so the current under rated conditions is going to be this. This is the rated torque that we have to supply, divided by that flux linkage rated 77.5 divided by 1.5, and that is 51.7 amps. There's the current that we need. We need to find the voltage. So the voltage equation is going to be RA times IA rated plus lambda AF R. This is the EA under rated conditions times the rated speed, 0.26 51.7 plus 1.5 times the speed, 103.7, and that is 168.9 or 169 volts. Therefore, the duty cycle is going to be the ratio of that voltage, 169, to the DC rated voltage, 169 over 294, and that is 0.57. So the rated duty cycle, 0.57. So this drive has a lot of extra capability when it comes to speed. We know that. Because we could run all the way up to this higher speed of 100, basically another 500 RPM. We can easily get out of this under no load conditions, and even with load, because the duty cycle 0.57 is much lower than 0.8. We could even run it at a load if we wanted. So that's B. So let's go to answer number C, the rated input power to the motor. Well, that's simple. So C, now that we know IA rated is equal to 51.7 amps, and VA rated is equal to 169 volts. Then the P that needs to be applied to the armature from the drive under rated conditions is 169 times 51.7. That better be bigger than 7.5 or we have made a big mistake. 169 times 51.7 is 8.74 kilowatts. So that is the rating of the drive power that has to be applied to the armature. This rating here establishes the rating of this thing here. So that part of the drive has a rating of 8.7 kilowatts in order to supply 7.5 kilowatts to the load. There's a fairly big difference there. So we'll understand why that is in answering the next question. So the final question asked is what's the efficiency of the motor. That's from the input power from the armature to the shaft. So quite simply, efficiency is output power over input power. And we're looking the total efficiency from that of the motor, so I'll just call it the motor efficiency, is the P shaft rated, this is under rated conditions, divided by the input power PADR, or PAD, under rated conditions, 7.5 over 8.74. And since you do it in percentage, you're going to multiply times 100%. And we can find the efficiency in percent. Let's see how that is. 86%. That's not very good. So that's the answer. Now let's go check everything to make sure that we haven't made a mistake. So a couple ways to check this. First of all, we've got the rated shaft power here, 72.3. This B omega MR is the loss. Now, here's a very interesting thing. We can find the mechanical efficiency right now if we want. So mechanical efficiency is going to be P shaft divided by P shaft plus the P rotational loss. That's the same as saying shaft torque times speed. Shaft torque times speed plus T loss times speed. So the speeds all cancel out, so you could just use these torques and check it. So we've got 72.3 over 72.3 plus 5.19, which you already know is 77.5. I want to multiply that times 100%. The mechanical losses of this thing, 72.3 divided by 77.5, so it's 93%. That's the mechanical efficiency. So this is a part of the checking the efficiency. And now let's check the electrical part of the efficiency. The mechanical efficiency is 93%. It's 93.3 actually, but 93.3%. The electrical frequency is going to be the power that is delivered, the mechanical power delivered to the shaft divided by the mechanical power to the shaft plus the I armature current squared times the resistance of the armature. So we haven't actually found P mechanical yet. We know that P mechanical is the rated mechanical torque times the rated mechanical speed, 77.5 times 103.7, which is basically 8 kilowatts. We can find it another way. The P mechanical is equal to the EA under rated conditions times the armature current under rated conditions. So the EA under rated conditions is lambda AF R times rated speed. And this is the current. 1.5 times 103.7 times 51.7, and we do. So we got that number. The the armature current loss, IA squared times RA, is 51.7 squared times 0.26, 695 watts. So the total input power, so the electrical efficiency would be 8 kilowatts over 8 kilowatts plus 695 watts. Now this is the number that we should have found anyway back in problem C, about 8.74. It's close. So I rounded some things probably, but I think we're close here. It's almost 700, so it's about 8.7. 8 kilowatts over 8.7 kilowatts. Multiply that times 100% to put it in a percentage. That's 0.92 or times 100 or 92%. So we got 92% electrical efficiency, 93% mechanical efficiency. So the total efficiency can also be found by multiplying these two numbers times each other. I've done a lot of rounding, but we should get close to the same number. 0.92 times 0.93 is 0.86 or 86%. And that is what we got. Yay. Okay. So it's really just a matter of, you can come at these at multiple different ways. And I'm trying to show you how you can break the problem down mechanically, electrically, how you can see the different, the same thing can be found in multiple different ways. You know, for example, here we were able to find the loss due to the torque, or the torque associated with the loss of the shaft. Okay, basically associated with the damping loss of the shaft. It's on 5 Newton meters, and because of that we could find the losses, the mechanical losses. We could also find mechanical efficiency. So we could have given you the mechanical efficiency, and you could have actually, if I told you that the only contributor to the losses was damping, or dampening, whatever you would call it, B, then you could find that number, B, from that. And the end game here is that you can use this number here in your dynamic model. So I gave you a bunch of mundane rating information, and it's helping you to populate a more cool simulation model that you can run to look at the dynamics of this thing. So that is this homework from problems 1 through 3. Problem 4 we didn't cover in class, so I'm going to show you that example at some point associated with another homework assignment.